In this video, I'm going to introduce you to the properties of viscoelastic tissues. As the name implies, a viscoelastic material is going to be both viscous, or containing liquid, specifically for human tissue water, and elastic components. Let's look at some of those differences. A perfectly elastic material would be shown on the left, and that could adequately be modeled as a spring. You deform it and it springs back into position. Figure B represents a perfectly viscous material. That is more appropriately modeled as a dashpot, or some sort of piston in which a fluid is being pushed through a cylinder. Figure C represents a viscoelastic material. Here we are going to put parallel both the viscous elements as well as the elastic elements. Figure D represents a completely plastic material that will deform upon being loaded. And then figure E represents all three in a particular tissue. If we look at a viscoelastic plastic material, we can say that once that tissue is deformed, it never quite goes back to its original dimension again, as you can see figure C being a little bit longer than figure A. But the fact that our tissues are not completely elastic, but are viscoelastic, means that some interesting properties are going to emerge. The first of those properties is going to be stress relaxation. With stress relaxation, we are going to apply a certain amount of strain to a material, and we're going to hold it there for a certain period of time. If we had a perfectly elastic material and we were to put something with a certain strain and just hold it there, and we were to go and we were to measure the amount of stress, say we had some sort of force transducers on either side of that material, we'd come back and we'd find that the stresses would be the same whether we came back in 5 minutes, 10 minutes, 5 hours, or 10 hours. But the fact that we have a viscoelastic material means that that stress is not going to remain constant with a constant strain. So we take a material, we stretch it to a certain strain, and we hold it there. And then we are measuring the stresses. And we come back a little bit later, and we're going to see that the stress is not quite what it was before, but it has declined. And we come back a little bit later, and we see it has declined some more. We come back even later, we find it declined even more than that. This property is known as stress relaxation. Stress relaxation tells us that if we hold the strain constant of a viscoelastic material, over time that stress is going to decrease. The opposite side of that coin of stress relaxation is going to be creep. With creep, we are going to keep the forces constant, and we are going to measure the deformation. So let's say that we had, once again, a perfectly elastic material, and we applied a load to it. And once that material is stretched, if we kept that load constant, the deformation would be constant throughout the duration that we're holding that force. Creep tells us that after we've applied that load, if we hold that load constant, over time that material is going to deform a little bit more, and it's going to deform a little bit more, and it's going to deform a little bit more. And so it's going to creep in terms of, let's say, what its length is if we're talking about a tensile load, but it's going to end up lengthening just a little bit more and a little bit more and a little bit more over time. And I hope you can appreciate that stress relaxation and creep are really two sides of the same coin. In one case, we hold the force constant and we measure the deformation, and we see the deformation is going to be increasing. That is creep. On the other hand, if we were to keep the deformation constant and we were to measure the forces, we would see those forces would be dropping, and that's stress relaxation. Our next property of a viscoelastic material is strain rate dependency. If we have a perfectly elastic material and we were to load that material, whether we load that fast or we load that slow, that a perfectly elastic material is going to apply the same resistance. Strain rate dependency tells us how quickly we load that material is going to depend on how that material responds. And with a viscoelastic material, when that material is loaded more quickly, it will be stiffer and stronger than if it's loaded more slowly. Our final viscoelastic property is hysteresis. Hysteresis is looking at the load deformation curve for both loading and unloading. And if we had a perfectly elastic material, as you see on the top, you'll see that the force deformation curve would be the same when we load it as it is when we unload it. With a perfectly elastic material, what you see happening is that the unloading or the return is not going to have quite the same curve that we saw with the loading. It's going to be less. Now, the area under the load deformation curve is energy. So, in addition to that material being less stiff when we unload it, the material is also going to return less energy than was put into it. So, that shaded area in the bottom curve represents energy that was lost to heat between loading and unloading. And that represents yet again another case where we say that no process is going to be 100% efficient. We can now apply this idea of hysteresis to cyclic loading. In this particular case, let's say that we look at several cycles of loading and unloading. You see in cycle 1, we have a certain amount of stiffness. We unload it, the material is going to be less stiff. If we subsequently reload it immediately, we'll see the material will be less stiff than it was when we originally loaded it in cycle 1. And then again, if we unload it in cycle 2, it's going to be less stiff than when we loaded it in cycle 2. And then if we immediately reload it in cycle 3, it's going to be less stiff than it was before ad infinitum. So there you have it. Those are some of the properties of viscoelastic materials.